Thank you very much. So we're all here because we're interested in this question of, are we alone in the universe? And there's been so many amazing planet discoveries in this past year. For example, the habitable planet around our closest star, Proxima Centauri, last August. The three TRAPPIST planets, if this is working. Yep, the three TRAPPIST planets that were also found in the habitable zone, and of course LHS 1140b. There's just been so many amazing discoveries recently, and so when we think about this, we're really talking a lot about these M dwarfs, and M dwarfs are much smaller than the sun, and you can see this kind of relative size depiction here. And from Kepler, we've learned that 1 in 4 M dwarfs likely have a habitable planet, and so we need to consider that these planets that we're going to be finding are going to be around stars that are very different from our sun. And so here's just an image of all the nearby known stars in our stellar neighborhood, and you can see that 75% of them are M dwarfs, and relatively few are G dwarfs like our sun. So one of the first things that we need to look at is, how does the star impact the atmosphere, the spectral fingerprints, and the biosignatures in that planet? And as we go, astronomers, for the non-astronomers in the room, as we talk about FGK stars, F are the bigger ones and M are the smaller ones. So I'm going to be using this terminology throughout the talk of FGK and M stars, G stars like our sun. And by and large, you're going from higher UV environment to a lower UV environment with some caveats, which I'll explain in just a second. So UV is interesting because it destroys some biosignatures, such as methane, in the atmosphere, perhaps making it harder to detect around a planet with a lot of UV. But on the other hand, UV produces some biosignatures, such as ozone, through the photolysis of oxygen. And when we look at reaction rates, we really see that it's the ratio of how much far UV to near UV that ultimately matters. And you can see this easiest in the production and destruction rates of ozone. If you look here, the production of ozone depends primarily on the far UV radiation, whereas ozone destruction can happen by near UV radiation as well. And going back to that statement I made earlier of these more massive stars have higher UV, it's really that they have a higher near UV because they still have that blackbody continuum flux in the near UV. And these lower mass stars have a much higher ratio of far UV to near UV flux. So this is what's changing the different atmospheres around these different stellar host stars. So when we also know that planets evolve from geology to plate tectonics and life, our own atmosphere has not stayed the same, and we heard possible things. We had things like the Hadean or the Archean snowball phases and the Jurassic period and other things in our Earth history. And so this is a nice little diagram that we're going to think that biosignatures are going to also change over this geological time. And going back to Jada's talk about possible hazes that we're going to see, or different chemistries that are happening in the atmosphere. So here you can see that at the formation of Earth, we think this is just a broad schematic picture. We don't have exact numbers for a lot of these things in early Earth history, but there was a lot more CO2 during the early Earth history. There was a rise probably of methane, given the longer lifetime of methane in the atmosphere without oxygen, and the biosphere being dominated by methanogenesis. And then oxygen sort of seemed to rise, broadly speaking, in 2 stages. So you had sort of this first rise of oxygen and then a later rise of oxygen to modern levels. And we heard about this in Sonny Harman's talk earlier in the session before lunch. And so if we look at I'm going to pull out 4 different time points that I'm going to talk about with you, how we could detect oxygen through geological time and considering these different star types. So the first one is looking at sort of a prebiotic planet. Something with higher CO2, some methane from volcanism, but not yet from methanogenesis, and no oxygen. And then also looking at things that are around 1%, modern concentration, so that PAL, you're going to see a lot as present atmospheric level, so that's 1% of our 21% oxygen after the great oxidation event. And then a third time point with around 10% oxygen, and then, of course, modern Earth with our 21% oxygen in the atmosphere. So if we look here, this is the oxygen A band at 0.76 microns, and this is just showing in the first column you see a prebiotic planet, then a 1%, again, modern concentrations, 10% PaLO2 in the modern Earth. This is for different star types, F, G, K, M, but we haven't yet considered things like surface reflectivity or the stellar impacts. And so this is just showing that we're using the same basic oxygen concentration for each. When we put this in a clear sky model where we're not considering clouds, but we are considering different effects in the atmosphere like Rayleigh scattering and whatnot for direct detection spectra, you can see that you see, is there a laser pointer on this one? I don't. Oh, sorry, thanks. You can see that you start to get that little bump for oxygen at 1% and 10%, and then the modern concentrations. Again, this color code is for FGK M stars, so the hotter stars are the purple lines going down to the red for the M stars. And when we add clouds, that feature seems to obscure quite substantially. So whatever little bump we add here, we don't really see it, and even for the 10% cases. And so this led us to think about, well, okay, what is actually happening with the effect of clouds on this spectra? And so just looking at the full Earth-like spectra, here in the visible, if we were to just assume 100% clouds at 12 kilometers, 6 kilometers, and 1 kilometer, that's what these lines represent. The dashed line is a clear sky model for Earth. The black line is 100% clouds at 12 kilometers. The red line is 100% at 6. And the blue line is 100% clouds at 1 kilometer. So you can see in the visible, for the higher clouds, it really does block a lot of the features below it, as we would expect. And it's a little different in the infrared. Here is again, for the 100%, 12 kilometers, 6 kilometers, and 1 kilometer clouds. The infrared differs because it also depends on the temperature of that cloud layer and where the species is sitting in the atmosphere and the temperature of the absorbing and emitting layer. Now, so if we look then, if we take out, what I wanted to do is just take out all the things that we were probably going to be able to correct for with telescopes. So we're going to be able to observe the star simultaneously, for example, but we're probably not necessarily going to know the surface reflectivity. So I left the surface reflectivity in, but I took out the influence of the star, assuming that we could completely remove that signal. And here then, looking at the situation with the light blue line is the 1%, the middle line here is the 10%, and the 100% oxygen case, this is for 0% clouds, and now we're going to go up to 100% clouds. And so you can see how the feature strengths are diminishing with cloud percentage for these different levels of oxygen. And of course, it's much stronger of an effect when you have less of it, and you see it's pretty much diminished for especially the 1 in 10% cases. So if we want to consider then ozone as a possible proxy, let's see how that is influenced by clouds. So we have the same setup with the prebiotic case, the 1%, 10% in modern Earth. And here you have already, with our clear sky models, we see these strong features of ozone, especially for the F and G stars early on with only 1% oxygen levels. And then, of course, the feature is quite strong going up until modern. When we add clouds, there's less of a diminishing effect of those clouds on the ozone feature. And I think this is most striking if you compare these two side by side with the oxygen feature and the ozone feature. This is assuming a 60% clouds, similar to what we have on Earth, with cloud layers at 1 kilometer, 6 kilometers, and 12 kilometers. You see here's the prebiotic case, the 1% PaL, the 10%, and the modern Earth concentrations. And you would be able to detect that presence through the ozone feature much earlier in Earth's history. And so if we look at also the detectability of O2 with LUVAR. Now this is using the coronagraph simulator that has already been, I think, mentioned 3 or 4 times in this session from Ty Robinson. If we look at this and calculate what are the rough integration times that we could get with LUVAR to detect oxygen with different cloud coverages and altitudes. So here we have increasing cloud coverages and different cloud layers. So you'll notice it's actually easiest to detect with a higher percentage of clouds, which might seem counterintuitive, but you get a higher signal with the added reflectivity. And if it's a low layer cloud, that oxygen's still above the cloud deck, and so you're going to increase your signal that way. Whereas if you have higher clouds and a higher cloud altitude, then it becomes harder to detect. And so the last thing I want to show you is looking at the biosignature detection then through geological time. If we just pull out things in the IR, here, this is, again, the 3.9 gigayear or so pre-life phase IR spectra for different spectral types. And if we go down to the 1% PAL case, the 10% PAL case, and the modern Earth case, we can see that the first combination, especially of biosignatures, is going to happen when you can detect possibly ozone in combination with methane in the IR, and you can most easily do this for these hotter spectral types for early levels of oxygen where you're going to get that production rate and be able to see those together. And then by around 10% PAL, you can detect it for a lot of different star types, and that's maybe one consideration we should consider when we're looking for these planets around other star types and at what geological phases we might be able to best detect life. So in summary, we know that the UV is going to be a huge player in the spectral type of the star. I think this really highlights the need we need simultaneous UV observations of these host stars. And after Hubble, without a UV mission, we need to do something about that because the UV dominates so much of our modeling. And for retrieval methods, this will really be vital for understanding. Planets will be at a wide range of different evolutionary histories. I just highlighted some things from Earth's own histories, but we're going to see such a huge range even beyond that. So we need to be considering those, as a lot of other talks have already done today. And also, clouds for oxygen, it might be a little sad, but you can still see ozone quite strongly throughout. So I'll stop there with any questions.
Thank you so much, Sarah. Please, if you have any questions, come up to one of the microphones in the center of the room. So we have some.
Hey, Sarah. Sean Domingo, Goldman, NASA Goddard. So if you had you're hinting that if you had a choice between getting the oxygen or getting the ozone, you'd go for the ozone given the clouds problem. But what if the choice is really oxygen with direct imaging versus ozone with the transit transmission measurement, where the clouds might become more of an issue for that kind of measurement?
So are you saying ozone in the
IR?
In the IR.
Yeah.
Yeah. I mean, whew.
I'm thinking, if it's a choice between like a JWST or an Origin Space Telescope, where you can operate in the infrared, but you're limited to transit transmission versus a UV vis direct imaging.
Yeah, I mean, it's hard because ultimately, as we've been talking, you kind of need both. And I'm going back to Sonny's talk on this, especially depending on what the level of abiotic oxygen could be reached and then what ozone level that could be detectable for these features, it might be ambiguous, even detecting the ozone as well. I think Vicky once said this. She's like, I want both. I want to detect the oxygen because that gives you an abundance, which is really useful. And we also want to detect, the IR features are just an easier place to detect molecules and gases. So I personally prefer the IR, but I do think ultimately we need the UV. So I also want I don't know. I want it all.
I sincerely hope we can give you both.
So, all right.
Okay, can you hear me? Okay. We have a few more minutes of time. So, yep.
All right, I'll just do this. So which aspects so this was looking at sort of Earth-like chemistries as we move away from planets that may not be like Earth, which aspects of sort of degassing chemistry or geology are going to affect the strength of that ozone signal?
The strength of the ozone in particular?
Well, so you were talking about ozone. So if the chemistry was different than the Earth, are there ways of putting reductants into the atmosphere that could change your ozone signal? So how could you model that as well?
Sure. So definitely depending, I think because ozone primarily comes from oxygen, so we're talking about how much oxygen could be there. So I'd refer you to several papers that have been done on this balance of, in fact, Sean Domingo Goldman has a great paper talking about the different types of reducing planet atmospheres and then where you can get how much oxygen you could get, and then you can use from that ozone as well. And so I would refer to Sean Domingo Goldman's 2014 paper.
Thanks.
Hi, Sarah.
Hi.
Nice talk. Good to see you again.
Good to see you.
So you said at the very end that you wanted simultaneous UV. Can you comment more on the balance between simultaneous versus contemporaneous UV?
Yeah, so I think with M stars that are flaring and having high activity levels, it would be really great to know kind of what's happening ideally at the same time. For stars that are quieter, like FGK stars, you probably can just get an idea of what's happening with the UV in general. I know there's some models that are trying to develop to how we get this for M stars, but with the amount of variability within M stars and also the extreme influence that has on our ability to tease out these false positives, especially, which tend to be predominantly for M stars, I want as simultaneous as we can get for UV, I think would be useful. If not, at least having an idea of how frequent are these flares, what is the states, the steady states between the flaring state and the quiescent state, so that we can use that into our retrieval models and make sure that the atmosphere is not changing quite so much in that time scale.
So you think then the response time is instantaneous from a UV flare, or is there?
It's not instantaneous. There's actually a paper that came out last year. I can send you the reference. I'm blanking on the name in my brain right now. Vanneau, I think, that looks at the hysteresis effective response times of the atmosphere after a flare, and I think it's like if I remember, 10 to the 7. I'm not going to say a number because I could be wrong, but there's some like lag time between these responses and then multiple flares and how it gets to a different atmospheric state.
Okay, thanks.
Let's thank Sarah again.